Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. And I am super happy to have Joe Masiero with us today. Hey, Joe.
Hey, thank you for having me.
Well, thank you so much for agreeing to talk about your very lovely article here.
It's exciting to be here, so I really appreciate it.
Yeah, great. Where are you located at, Joe?
I live in Burbank, California, just outside Pasadena.
Burbank. Very awesome.
Yeah.
And it is January 12th of 2022 as we shoot this. And I imagine there's no snow on the ground in Pasadena or Burbank.
No, it was 80 yesterday, so it was beautiful weather.
Yeah. I'm in Phoenix, Arizona.
Okay.
We got pretty warm yesterday.
Yeah.
We get a little chilly in the morning, but it heats up well. And you have a very awesome bookshelf behind you. You got all kinds of doodads, and I see something with a globe that says Violet on it.
Yeah, that's my wife's. It was a going away gift from her last work. She works with international students. So
very cool.
Yeah.
Very cool. Very awesome. Nice collection there.
Thank you.
So Joe, what do you like to do for research?
My research mostly focuses on trying to understand how our solar system formed by looking at the minor planets. So the asteroids and comets, the small leftover bits that are scattered around our solar system, and trying to figure out what they're made of, where they're going, what's happened to them in the past, and what will happen to them in the future.
Super. And that is going to bring us to this very awesome Planetary Science Journal article, PSJ, open access, people. Asteroid diameters and albedos from NEOWISE reactivation mission years 6 and 7. And Joe, take us away.
Thank you very much. And this is work I did with all of my co-authors on the mission. So showing up here, Amy Meinzer, James Bauer, Rock Kutry, Tommy Graf, Emily Kramer, Yana Pitichova, and Ned Wright are the listed co-authors, but this is a spacecraft mission, right? This is a team, not just of the scientists, but there's hundreds of people in the back who've contributed over the course of the entire life of this mission, probably thousands at this point, to making this a success. So, just want to acknowledge them too. Not everyone's listed on the papers. There's a lot of people who helped make this happen.
Cool.
Yeah. So this work is taking the, so let's start with NEOWISE. What is NEOWISE? NEOWISE is the Solar System Identification Mission. So it's a mission using an infrared space telescope to detect and assess hazardous asteroids. So looking for objects, asteroids and comets that come close to the Earth, finding them and characterizing them, figuring out what they are and how big they are. We do this using the WISE spacecraft, which was launched in 2009. And so the history of this mission was WISE was launched as an astrophysics mission, surveyed for 7-8 months, ran out of cryogen, was continued as a planetary science add-on. This was the NEOWISE phase of the original mission until 2011.
Okay.
And then was put in hibernation for 2 3/4 years and sat there just orbiting the Earth, not taking any data, not doing anything. And in that time, we were able to, one, show how useful the data was, even without the cryogen, for finding and characterizing near-Earth objects.
Okay.
But also, Chelyabinsk hit. And so there was a whole renewed interest in trying to figure out, let's see what other resources we can bring to bear on finding these hazardous asteroids.
Cool.
And so in December of 2013, NEOWISE was turned back on and began surveying again. And we've been working since then. We originally started as a 3-year survey in 2013. In December 2013, it was supposed to just go for 3 years. And we've been getting extensions and extensions as the mission has continued to perform, because originally we thought it wasn't going to survive more than 3 years.
Yeah.
But the sun was really quiet. Between 2013 and now, the sun has been incredibly quiet. So that means the atmosphere wasn't puffy, so the orbit was stable. And so things were pretty good for a lot longer than we expected. And at this point, we are scheduled to continue surveying through June of 23.
Awesome.
So yeah.
Okay.
Yeah. So for this mission that was originally only supposed to go for 7 months to now be in, the 9th year of reactivation and the 13th year of, flight it's pretty awesome. It's really exciting. I joined the mission right after launch. So right before launch, rather 2 months before launch, I signed on as a postdoc with the WISE mission, and I've been involved ever since. And so it's been a real fun ride. I've really enjoyed it. Yeah. Very
cool.
So, so NEOWISE is basically just the reboot of WISE using the WISE spacecraft. And so WISE is a small 40-centimeter telescope, 2 infrared channels in orbit around the Earth following the day-night terminator. So it tends to look straight away from the Earth when it can. Originally, it was 90 degrees from the sun, and so it was just sweeping rings of the sky. As our orbit has changed, the orbit's precessed, and so now one side is 20 degrees farther, is at 110 degrees from the sun. The other would be looking 70, but we can't look that close to the sun, so we point at 90 from the sun and take the extra heat load from the Earth. Okay. So this is how the survey has evolved over time, but we're basically just constantly sweeping circles. Every 90 minutes, it does another orbit of the Earth and takes another scan of data. Constantly. Again, this is the great part about space missions, right? No weather, no downtime, no day-night cycle. You just keep going. You're going. Yeah. And so we're taking data simultaneously in 2 channels right now, 3.4 and 4.6 microns. It's nice that so it's a beam splitter, right? So you do get true simultaneous data. You get 2 colors on everything, and that's really important for figuring out, what has the color of a star, what has the color of an asteroid. You can basically get a rough temperature gauge just from those 2 bands simultaneously. And it's that 4.6 micron channel in particular that's where we sense the NEOs. You're on the Venus side of the distribution there. They're close enough to the Earth that they're hot enough that you get a decent amount of thermal emission at that wavelength. And then some of the NEOs actually get some thermal emission in W1. For W2, for farther objects, like when you get out to the main belt, out beyond Mars, you don't get as much thermal emission anymore. And so it becomes harder for us to detect them. So the majority of the objects we've seen since we ran out of cryogen have been the large main belt asteroids that are just seen in reflected light because we see them all the time. But all the stuff we see in when you see something that's bright in W2 and not there in W1, you already know that it's hot. And you already know it's close to the sun. And so you can already get a real quick handle of, this is likely to be an object of interest. Yeah. Very cool. Yeah. So, I mean, it's a lot. And the scan is nice in that it has a 10% overlap. So as it goes through this, stripe on the sky, there's overlap every 11 seconds. And so there's short exposures, but between the overlap between them, you basically have good calibration across the whole scan. Scans have overlap between them. And so you build up this nice, well-calibrated, photometrically stable system across the sky. And now that we have, 8 years of data, of previous data just from the reactivation survey and data from 2010 in the cryo survey too, you have a lot of, constraints for what photometrically should be going on, astrometrically should be going on. Good. Yeah. So once we take the data, as I mentioned, right, we have this, you can tell instantly from the color, right, that something is warm. And so this is where we get into our thermal modeling, right? And so this is what we try and do then is say, if we're looking at the emission from an object, what can that tell us about the physical properties of the object, in particular, the size? Typically with a ground-based telescope, when you discover an asteroid, all you know is roughly how bright it was when you saw it, which is a combination of size, distance, and reflected light. And after you've observed it for, a couple of weeks or so, you have a rough orbit. And so you know how far it was from the Earth and from the sun at the time of observation. And this is something that's, unique to solar system astronomy that all the other astronomers don't get to deal with. After about a month, the distance to an object to, a couple kilometers. That becomes not your main point of uncertainty, right? Absolute distances. And so then for reflected light, once you have that absolute distance, you still don't know if it's big and dark or small and bright. If you're looking at a bowling ball or golf ball, because they'll reflect about the same amount of light. With thermal emission, what we're seeing is sunlight warming the object, heating it up, and then it re-radiates that as heat. And so because we know how far away it is, and we know what what the orientation of the sun is, and so basically what the warm hemisphere looks like projected to us, and we know the temperature because we know how far from the sun it is, all of a sudden we're left with just how bright is it is how big it is. Okay. Yes. And so that bowling ball, golf ball, the warm bowling ball emits much more than the warm golf ball. Okay. And so this is how we can basically, so what we're doing now is we're taking these, spherical Cal models and making some simplifying assumptions about what that, heat re-radiation looks like. And then you can scale that model to fit your observations. And that gives you the spherical equivalent size to within a fairly tight margin. And this is something that you can't get any other way, at least easily. I mean, you can radar observations where you bounce radar waves off the near Earth objects. Those are fabulous for size.
Oh, yeah.
but you have to wait till it gets within, a fraction of a lunar distance often. That doesn't happen often. You can do occultations, but again, you have to have a coordinated set. You have to wait for it to pass over a star.
Yes.
So for, surveying diameters of objects, infrared is the fastest and easiest way.
Nice.
Yeah. So this is, this is the main benefit of doing this thermal modeling, right? And so we use something called the NEATM, the Near Earth Asteroid Thermal Model, which is basically just taking this beaming parameter, this eta value, which it accommodates the differences in the surface temperature distribution from what our spherical model is assuming.
Okay.
Right? And so some of it is that the model assumes there's no night side emission, right? 0 Kelvin on the night side, which is clearly wrong. But it generally works for most objects unless you're getting really high phase observations.
Yeah.
If you're looking at crescent phase, that kind of goes out the window. But for high phase observations, for low phase observations rather, it works pretty well. And so this, so now we're just trying to account for, is surface roughness changing the way the thermal light is being absorbed and re-radiated, right? As if you assume a perfect sphere versus one that has craters on it, the craters will warm up on, on some sides, the subsolar sides more than others. And so this is kind of a catch-all because we get a few points of data. We have 10 data points for most of these objects in 1 or 2 bands. This is not, if you can get multiple epochs, you can start to do very complicated thermal models. But for these snapshot observations, having a high fidelity model would be overfitting the data at this point. And so this is kind of the survey fit using this, this simplified model. And, one of the main simplifications is we're assuming they're spheres, right? Asteroids are not spheres. And we've seen this time and again. Every flyby, they're lumpy potatoes, right? And so the size we're getting is if you kind of took that lumpy potato and smushed it into a sphere, what would that general size be? So it's this spherical equivalent size, effectively. And so, some asteroids we've seen on comets are highly elongated, right? Oumuamua was, 6-to-1 axis ratio or something. And so what does that turn into a spherical equivalent? And how do, so there's a lot of assumptions you have to make and a lot of, if you get this elongated object and you're always seeing it in one projection and not over the full rotation, you'll have offsets in your fits.
Yeah, right.
So there's a lot of caveats to this, but the benefit is you can do this for hundreds or thousands of objects quickly.
Right.
And this kind of work then allows us to say, okay, A, what does the population distribution look like? But then B, what are the weird things that need follow-up?
Right, exactly.
Right. And so that's the main goal of this, is trying to characterize what this population is doing, right? So that when we start getting things like a hazardous object that we don't know about, what instant guesses can we make about it before we get any other data based on the population understandings that we've learned from things like NEOWISE?
Informed guess.
Right, informed guess, exactly. And and so it helps lead to the next step. And this is something that we do pretty regularly with the Planetary Defense Conference. Every couple of years, they have a Planetary Defense Conference where they do a exercise where a theoretical impacting object is discovered, and everyone in the room war games what you would do, what data you would get to characterize it over the 6 months, which are played out over the 4-day conference.
Oh, that's cool.
Yeah, it's a lot of fun. And so the most recent one, a couple times it's been, NEOWISE picked it up, and all of a sudden the uncertainty went, from pretty large to, even though the impact uncertainty doesn't change, what we can do is, if we can rule out all the big solutions, now you went from not knowing if you're getting a minor impactor versus a dinosaur killer. If we can rule out those big ones, that changes the whole tenor of how you have to respond to it in the future. So that's that's one of the reasons we're doing this, right? And one of the reasons we keep this survey going is not just discovery, right, but characterization, primarily trying to understand as many of these objects as possible. And so so this paper was specifically focused on years 6 and 7 of our survey. We had previously published the first 5 years in earlier publications. We just completed the year 8 data, and we're in the process of at IPAC getting ready to release that. Yeah. And so that will be released, I think March timeframe is what the scheduled release date is. We have annual data releases of these. But we try and publish our results in a fairly block fashion fairly regularly to get those sizes out there so the community can use them. And so that's the results that we're showing here, right, in the next section are I think, so there's section 4 is our results, and So we include our tables here. This is just the first 10 lines. Obviously, one of the lovely parts about PSJ is you can just put your snippet of table, and because it's an online journal, you can just click and it takes you to the full table. Because the main belt tables here are 5,000 entries each. Even the asteroid tables are, a couple hundred, 200 each or so.
Oh, okay.
Yeah, lots of data, and so we give the sizes, we give the reflectivity, the geometric albedo PV there, assumed beam parameters, how many times we saw it, and what phase we saw that, especially for the NEOs, that becomes important. If you saw it again at high phase, that the models are not as solid at higher phases as they are at lower phases. So it helps you kind of adjudicate how, which ones might need to be looked at again in the future, right? But I think, it's important that we go through and present all of the observations fit with the same model at the same time with the same brush, right? Not trying to baby each one, but to say, here's what the whole thing says, because then you have a population you can, yeah, exactly. You can do comparisons against that, right? If you know everything is fit the same, then okay, this is what this outlier means. This is what that one means.
Nice.
Yeah. And so, we list our tables here, mostly for form and function to show the reader what they're going to be getting when they download the machine readable one. Because no one...
Remind me what an MBA is.
Main belt asteroid.
Main belt, thank you. I'm good.
Yeah. So this is, these are one of the ones that, most of the stuff we see, because these are most of the, there's over 1 million known main belt asteroids now at this point, and 27,000 near-Earth objects. So most of what you see are the main belters, and that winds up being the background population you have to pull the NEOs out from.
Right. Yeah.
Yeah. And this is going to become an interesting problem for the next mission I'm working on, the NEO Surveyor mission, because it just goes even crazier with this, main belt background population. But yeah, so but when you take all this data and you put it together for the NEOs, you get figure 1 here. And so this is kind of the main result. This is adding together all 7 years of data that were published so far.
Cool.
And so this is showing diameter versus albedo, visible geometric albedo. Again, not bond albedo, but the geometric albedo is the ratio of what the reflectivity you observe versus the reflectivity in an ideal scatterer, right? It's a little bit different, but I like to think this geometric albedo is what your eye would say the albedo is.
Yeah.
Right. Versus bond albedo is disk integrated and covering multiple wavelengths. And so it's, a little less intuitive. But what we're showing here is the cyan points are all the things that were detected or discovered by a different survey that passed through our field of view that we were able to characterize. Okay. The black points are ones that were discovered by our survey. Cool. And so we put error bars on the discoveries. All the objects have about the same similar sized error bars, because most of the errors here are driven by model uncertainties. So in diameter, it's model uncertainties. In visible albedo, the majority of the uncertainty is coming from the uncertainty on the reflected light measurement, or it's about a 50. It's about an even blend between the reflected light measurement and the diameter model uncertainty, but they're roughly about the same. It's hard to get better than that.
Is this span in diameter, is this a selection effect? Like you're not sensitive to the super small ones or the super large ones, or? Yeah, so there aren't too many near-Earth objects bigger than 10 kilometers. Okay. There's a handful, and we've seen them a couple of times, but I just cut the plot off there because there's not a lot going on. I think there's one off at 40 and one off at 20 or something. So there's not much bigger than 10. On the small side, yes, absolutely, that is absolutely selection effect. The nice part about a thermal infrared survey, because you're looking at the heat radiated, you don't particularly care that the temperature does depend on the reflectivity of the surface. A black surface is hotter than a white surface, but not that much on the larger Kelvin scale. And so dark and bright objects are roughly the same brightness as a function of size and distance. And so we are effectively a size limited survey. Okay. As opposed to ground-based surveys, which are a magnitude limited survey, right? So they're reflectivity limited. And that's what you're seeing here, is that vertical cut right around 150 meters or so, where our selection just drops off pretty hard. That's just because you have to get something really close to pick it up. Yeah. Right. Otherwise, that's kind of where our cutoff is. But the over density of black points in the bottom corner, like basically between 200 meters and a kilometer,
and this low albedo range and the couple percent albedo.
Yep.
The reason we're discovering things there and not in the upper cloud is because the cutoff for visible light telescopes is a diagonal line on this. And so it would run from the top left to the middle bottom. And so that's what a limiting magnitude survey does to you. And so all of those black points in that bottom left corner are just the phase space that is below the detection capabilities of the the reflected light telescopes.
Yeah. Okay.
Yeah.
Good.
And so, we're able to put these on a plot. This is why we're discovering mostly dark objects and mostly big objects, right? We're finding things that are in the kilometer range still. Still discovering, there's not too many of those that are unknown, but there's still a few floating around, and we're still able to discover them because they're low albedo. They're these typically, they look like dead comets. They're on eccentric orbits. They don't come around very often. They're hard to pick up with the visible light telescopes when they do come, but they glow brightly in the infrared. So we pick them up.
Cool.
Yeah.
Very cool. I like Very nice.
Yeah. It's and so basically every year we do another survey, we just add more points to that plot. And so you can see that bimodal distribution there, right around 10% albedo. There's like a cloud above it and a cloud below it, especially in the cyan points. That's real, right? And that is, we've seen this in the main belt. We've seen it in all the NEOs in the cryo survey, and now the NEOs in the post-cryo survey, that there are two different classes of albedo objects, right? These silicate-rich ones and the ones that have carbon-rich surfaces.
There we go.
Right? Yeah, this S types and the C types. And that plays out in these albedo distributions, right? And when you do the histogram of this, you find about 2 objects in the upper cloud for every 1 object in the lower cloud. For the near Earth objects, for the main belt, it actually changes as you go through the belt, and so it's about 50-50 in the inner main belt. In the outer main belt, it's about 80% dark.
Yeah.
And so this is already leading you to, okay, these NEOs are not drawn evenly from the whole main belt, but there's selection effects and certain subregions that are being drawn from to get the distribution you're seeing here.
Cool.
Right. So yeah, this is the main point of this paper, is filling out this plot, but we did some other analyses as well, right? And so one of the things you want to do is figure out, how well do you know this, right? We have our statistical uncertainties, and we know from our model, if we just vary the model parameters, we say, here's one of the input parameters, here's our uncertainty on that input parameter. So run a bunch of Monte Carlos with all of those to see what your statistical uncertainty is, right? And so that's where we get these statistical uncertainties from. You Monte Carlo your assumed parameters, you Monte Carlo your measurements within their measured errors, and you get this. But that can't account for that big uncertainty of that, how real is the model we're using. And so you have to do some other meta-analyses to try and pull out that, to basically characterize, is there any bulk shift in this, right? Or is there something else we're not, are those assumed parameters, the parameters we're assuming that we're just varying over some window, is it structured within that window? Are there correlations? We can't model that now. So we look at these, on the back end, taking the fits and saying, okay, what are the results of that? So the next plot was, it was one suggested by one of the referees. Yeah, they're helpful, it turns out.
All right, the peer review process worked. Excellent.
And so this is, so just inspecting the statistical uncertainty that we fit for the diameter compared to the phase angle we observe the object at. And so this is it. It took a little while to parse this one because it was kind of unexpected, right? You would expect that from what I said about the model, right? In that, as you get to higher phases, the assumptions break down. You would think that the uncertainties would go up. Not down. And so
at least stay constant.
Yeah, and so what you're seeing here, so above 50-degree phase, you're getting this basically constant behavior. And so that's the model, that's the uncertainty inherent to the model, right? And so as you're getting to the weird phases, yeah. Right. So that's what's going on there. At smaller phases, you get this larger uncertainty here for a different reason. And that's because, so when I talked about the survey, right, NEOWISE is at a fixed solar elongation as it surveys. And this has this weird effect of basically your viewing geometry is fixed. So the farther away from you an object is, the farther away from the sun it is, and the lower the phase angle is. Right? If you're looking at all kinds of elongations, you could see a low phase angle object close here. You could see a high phase angle object far away over there. Here we're fixed. And so phase angle is effectively a function of distance of observational distance to the observer, which is also a function of distance to the sun. So these three are tightly correlated. That triangle, because there's that right angle in there, that triangle doesn't have a lot of play in it. Yeah. And so what you're seeing here is as you get to phase angles below 40 degrees or so, you're getting objects that are farther away from the Earth, which is farther from the sun, which is colder. So it pushes you the thermal peak farther from W2 and causes more uncertainty in basically on the Wien side. Small changes in the temperature cause big changes in the expected W2. So your statistical uncertainty goes up as you get to smaller phase angles for the near Earth objects here.
Interesting.
Yeah. And then it turns around as soon as you get back to the main belters, when you go far enough away, it kind of just collapses and it doesn't become as big a problem anymore because your phase angle range is so much narrower. You can make different assumptions about the input parameters. But for the near Earth objects, you get this, this strange behavior. So that was a lot of fun. And again, I thank the anonymous referee for the helpful contributions.
Cool.
So, that's kind of understanding our statistical uncertainties, but, the systematic uncertainties are also a concern, right? That if we made an incorrect assumption about the model, that is going to cause a bulk shift potentially, and that won't show up in our error bars. And so figure 3 is basically this analysis of that. So in figure 3, we took our diameters we measured in the first 7 years for near Earth objects with the reactivation data and compared that to the same objects seen during the cryogenic phase of the mission. And the nice part about cryo here is that cryo had multiple thermally dominated bands. And so beaming parameter typically wasn't a variable. It was better constrained, or even if you only had a single measurement, it's at the thermal peak, right? And so that doesn't change as much as, on that quick fall off side you get at shorter wavelengths. And so that helps us adjudicate, are we making good assumptions about the beaming parameter, about that flexible parameter? And, what we find is that, you can see in that third panel there, that the offset between the two is around 4%. So we're pretty good. There's a systematic offset of maybe 4% smaller. But, the width of that distribution is 30%. So that tells us that we have a statistical uncertainty of about 30% from the diameters we measure, but that there's no systematic offset, no significant systematic offset.
Yeah.
And we've done this analysis previously using main belt asteroids, again, because we see them all the time, and we had a lot of them in cryo mission. But this is our first opportunity because now we had 7 years of near Earth object data to do an NEO to NEO comparison from reactivation to cryo. And now we had 83 objects with 100 and something different epochs. And so we're able to actually have enough statistics to do something. But, and then there's the concern, right? So now we're looking at how sensitive the model is to where on the thermal emission you are, but we're still using the same model for these two fits. So figure 4 is saying, okay, let's compare our measured diameters here against diameters from a completely different method. In this case, asteroid radar observations, where they have done 3D models of the shape. You have a really good idea of what the shape is and the effective diameter. As I mentioned before, because you have to wait till these things get really close, it's hard to get the observations, especially harder now that Arecibo is no longer with us. Yeah, that was real sad. So we only have 11 objects, I think, in this set, on this overlap set here. But you can see, and again, small number of statistics, but we're not seeing a big systematic offset in that third panel. And the standard deviation is about the same, a little bit bigger, which is what you would expect that, comparing against a different kind of model, you get a little bit bigger, or maybe it's small number statistics, but it's consistent, right? It's not wildly off. We're not seeing, atrociously different things. So it's, this is really comforting to say that, we are constantly evaluating our model to make sure it's actually doing what we think it's doing, so that we have faith in our population studies that we're basing our data on. So yeah.
This is nice. It's telling a coherent story. Let's put it that way.
And again, it's a big benefit that a space mission, our detectors have been incredibly stable over the life. We've seen effectively no change from launch to today for the W1, W2 detectors. So space is a lovely, stable environment if you do it right. It's scary when things go wrong, but it's lovely and stable when things go right. So one of the other cool things that had been tickling at the back of me, we've been surveying for 7 years, and when I wrote this paper, we've been surveying for 7 years at this point. And as I mentioned, W2 is great for seeing near Earth objects. We get a lot of thermal stuff. It's great, but we're only a 40 centimeter telescope, and so when you get out to the main belt, we're seeing mostly reflected light. We are significantly smaller than the 1 to 2 meter telescopes that are doing the majority of asteroid surveys. Yeah. So we should be discovering nothing in the main belt. Right? We shouldn't be finding anything new because we're tiny, and there's other surveys with bigger telescopes constantly surveying, and yet we still were discovering objects. And so there was a why. How are these things still available for us to find? Okay. And so that was what this kind of secondary analysis was just trying to figure out what made these special.
Yeah.
And so I took all the main belters that were listed as discovered by NEOWISE and the reactivation. So without cryogen, because NEOWISE was fabulous with cryogen. With W3 and W4 band passes, we discovered 30,000 objects in 7 months. So long mid-wave surveys are fabulous for finding asteroids. But shorter, so like the 4.6 micron shouldn't be good. And so I just plotted everything up. And, the first top left plot here, you see, okay, everything has high eccentricity and has a perihelion getting close to the line for Mars crosser near Earth object, right? So, okay, what you would expect, more elongated objects, more elongated orbits. When they get into perihelion, they'll be hotter, and maybe there's enough thermal emission to really pick up in W2.
Yeah.
Mm-hmm. That kind of makes sense. But then at that bottom right plot, you see that there's some objects with perihelion distances out at, 2 and 2.2. We discovered one thing at 2.6 AU, and but there's no right we should be finding that object, except that it's at high inclination here.
Right. And
the plot above that, if it's noisy, but if you stare at plots of the main belt asteroid distributions for a long time, you'll see that the two clumps at right above there, the clumps at 3.2 semi-major axis and 25-degree inclination, and at 2.2 and 25, those are associated with two major asteroid families, the Phocaea and the Euphrosyne families.
Sure. Okay.
And as I show, so we said, okay, what else about these is special, right? So if you go down to the next figure 6, we now looked at the angular elements for the orbits of these objects. And, so longitude of the ascending node, this shows this structure here that is actually what is expected. That's what the whole solar system looks like, that's imprinted by Jupiter. The one below that, longitude of perihelion, same thing, that curve, that single moded curve around 0, that's just because of Jupiter. So all the asteroids show that. But the top right plot should be flat for, if you just took a random sample of main belt asteroids, that's flat. And here we're not seeing it. An argument of perihelion is the angular distance between the ascending node and the perihelion point. And so having two clumps near 90 and 270, what this implies is that these are objects where their orbits are such that perihelion is as far out of the plane as the object gets.
Wild.
And so if most of your surveys are looking near the ecliptic, which is where most surveys should look if you want to find stuff, you're going to find that you'll get an even distribution of everything, but you're going to miss things that only get bright when they're close and far off the plane. And so from Earth point of view, tend to be at very high or very low declinations. A benefit of being in all sky surveys, we do find stuff in the south just as often as we do in the north. And so since most of the major asteroid surveys are in the northern hemisphere, there's a lot of phase space in the south. Now Atlas is turned on, and there are more surveys now coming online in the south. And then as soon as Vera Rubin turns on, that's going to switch the problem, and all of a sudden you'll know all about the southern half of the sky. And the asteroids that only show up at perihelion in the north will be harder to find. But for now, what we're finding is these objects that get close to the sun when they're far from the plane.
Yeah. Wild.
And so there's a few scatter plot. The next plot is just a series of scatter plots looking for correlations between the argument of perihelion and various other parameters. And the main interesting one is the bottom left figure G, subfigure G, is you can see that weird like sawtooth function there where the declinations are getting down to -60, right? So this is where we're finding these things at above 40 or below -40 degree declination. And so that's what's going on here. And then if you go up to subfigure B here, this just shows again that all of those high perihelion objects we're discovering are, as you get to higher perihelion distances, the clustering just narrows down to those two fine points right around 90 and 270. And so that's effectively what's happening, is we're finding things that only get close when they're at extreme declinations that are outside most survey windows.
Very cool.
Yeah. So that was kind of the main thrusts of the paper here, is just taking the next 2 years of data and figuring out what we can learn from it, both about the near-Earth objects, but about other objects, everything we observe. And I'm really impressed that all of these data are being released publicly annually. And so there are, I think, over 2,000 papers now using some facet of NEOWISE data one way or another. And I love survey data because you just look at the plot of papers over time and it just keeps going. It just goes up and up and up and up. And we saw this with IRAS, and so we expect it with WISE. So it's the reason that we should be doing surveys and making sure the data are public as soon as possible, because the community really loves using it. And there's a lot of cool stuff hiding in that data.
Well, I certainly like that plug for open data, open knowledge.
Absolutely.
Very cool. Joe, thank you so much for walking us through this very lovely PSJ article.
You're very welcome. Thanks.
Sure. And I lost my control here for a minute, so we'll just go in this mode till I figure this out. Okay. So you touched on it a couple of times about where the future may lie. On VRO or other things like that. So where do you think we go, let's say, over the next couple of years with NEOWISE or others? There's clearly going to be more observations. You already mentioned years 8 and 9. Do you expect to have years 20 and 21 from NEOWISE?
No.
I'm just firing. Are there considerations of, and I understand once you say non-spherical, that opens up, an enormous, pile of, okay, it's not an elephant. So, okay, what does that mean? But, you could do elliptical.
No, and
as opposed to spherical. So, are there tests in the modeling? So just kind of,
yes.
Where do we go over the next couple of years?
Yeah. So, I mean, one of the things, NEOWISE is getting new objects, discovering new objects, is characterizing objects we haven't characterized before, but it's also providing repeated coverage of objects we've seen multiple times. And to do what you're asking, that's what you need, because from that single snapshot, you don't know, right? There's a lot of unknowns, and so you really have to assume a sphere. Only when you've seen an object from this side and that side and that side and that side, now you can start building up what the 3D shape is, right? So every time you added, by adding in 3 more axes, going from a radius to an ABC, you need a whole lot more data, right? Once you need to know its rotation. So by getting these multiple observing epochs, that's exactly what we hope to do in the future.
Cool.
For NEOWISE, right now we're scheduled to continue survey through June of 23. Things are stable. The atmosphere seems quiet. However, our current estimates for the reentry date, I believe, are early 25, late 24, early 25. So that will be a somewhat hard limit for when we can continue observing. But so that will be possibly, so right now we have year 8 data in the pipe, in the bag, and are getting ready to release it. Year 9 data is being taken right now. That will end December of 22. And so we'll have year 9.5 data. Could we continue? Possibly. It really depends on the health of the spacecraft. It's over 10 years old now. It's just a fingers crossed and hope nothing goes wrong. But as long as it keeps behaving, we want to keep flying it. But the next big thing is NEO Surveyor.
Yes, right? There you go.
And so that's the main big thing. And so that's the mission we're working on. Current launch date is going to be early 2026.
Cool.
This is specifically designed taking all of the lessons we learned from NEOWISE about what worked and what didn't, and saying, instead of taking an astrophysics mission and using it to find asteroids, what if you designed an asteroid hunting telescope? What's the ideal telescope to look? And that's NEO Surveyor. 2-channel thermal infrared, 3-minute exposures instead of 11 seconds, stop and stare dwell, large field of view, off axis, so there's no diffraction spikes. And so the whole thing is being designed, a whole bunch of sub-images to get rid of cosmic rays. The whole thing's being designed so that to be optimized for finding moving objects. And we're anticipating something like 8 million main belt objects and 300,000 near-Earth objects.
Wow.
And because it's infrared, every object we observe that gets in orbit, we'll be able to get a diameter for. So it won't be just, here's an orbit and that's the end, that's all we know. It's here's an orbit, here's how big it is. And if Vera Rubin provides an optical light point, here's how reflective it is. And suddenly you have this census of the small bodies of the solar system. So that's what I'm really looking forward to. And the interplay between Rubin and Surveyor is going to be great because they cover fundamentally different parts of the sky. Surveyor looks from 45 elongation to 120. Vera Rubin can look down to 65, but I think most of their survey is going to be, in the, plus, 90 and above. And so it really will cover, 3/4 of the sky, be able to follow these objects around for, majority of Earth's orbit. It's going to be awesome.
It's going to be very cool over the next couple of years to finally get a real handle or better handle on this amazing population of small bodies. It's very cool. Very cool. Joe, thank you once again.
Thank you very much, Frank.
And that'll do, everyone. And I hope this makes your astronomy day just a little bit better. And we'll see you on the next one. Bye-bye.